Have you ever stopped to think about what's really going on inside the computer chips that power, well, literally everything in our lives? We're about to dive deep into that hidden world, this incredibly high-speed dance of physics inside semiconductors, where electricity moves in ways that are both strange and, incredibly powerful. Now, that phrase right there, a rock we taught to think, it sounds like something straight out of science fiction, right? But it's not. It's just physics. And in this explainer, we're going to break down the fundamental principles that let us take a simple element, silicon, and control the electricity inside it so precisely that we can turn a rock into the brain of our digital world. So here's our game plan. First, we'll look at a semiconductor when it's just sitting there, perfectly at rest. Then we're going to get things moving and explore the two main forces that make charges flow. After that, we'll need a new language to describe that action. Then we'll get real and look at the actual speed limits they face. And finally, we'll wrap it all up into one unified, powerful model. Okay, so where do we even start? Well, before a chip does anything, before it processes a single bit of information, it's in a state of perfect balance. We call this equilibrium. And to really get how we control electricity, we first have to understand what the system looks like when it's not doing anything at all. The most important idea for this state of balance is something called the Fermi level. Now, it's a concept from quantum mechanics, but honestly, the water level analogy is perfect. Just imagine a big tank. Below this water level, every available spot is filled with an electron. And above it, they're all empty. In a perfectly calm, balanced semiconductor, this water level is completely flat. So here's where we take control. There's this process called doping, where we intentionally add specific impurities into the silicon to tweak that water level. If we add atoms that have extra electrons, that raises the water level, making it super easy for those electrons to start moving. But if we add different atoms, we can create holes, basically spots where an electron should be. This lowers the water level and makes it easy for those holes to move around. And this ability to raise or lower that level, that is the fundamental trick behind every single transistor. All right, so we've figured out how to set the water level. Now it's time to make some waves. Let's kick the whole system out of balance and see how we actually get these charges to move. And it turns out there are really only two fundamental ways that this happens inside a semiconductor. The first way is called drift. This is the one that's probably most intuitive. You apply a voltage that creates an electric field, and that field literally just pushes the electrons and holes along. It's kind of a brute force approach, like a powerful river current just forcing logs downstream. Now, this second method, diffusion, this is what makes semiconductors so special. Imagine you have a whole bunch of electrons crowded together in one tiny spot. They don't like being crowded, so they will naturally spread out to areas where there are fewer of them, just like a drop of ink slowly spreading out in a glass of water. And that movement, driven by nothing more than a difference in concentration, actually creates its own electrical current. And, this difference is absolutely crucial. Drift is just a forced push, something you can get in any old copper wire. But diffusion, this natural tendency to spread out, that's the secret sauce of semiconductors. Our entire digital world is built on the incredibly delicate balancing act of playing these two forces against each other. So, what happens when you have both drift and diffusion happening at the same time? Well, that single, nice, flat water level we started with, it's gone. The system is now in this dynamic, active, unbalanced state. And to describe what's going on, we actually need a whole new language. And that new language gives us what are called Quasi-Fermi Levels. The idea is actually pretty simple. Instead of having just one water level for everything, we split it. We now have one distinct water level just for the electrons, and a completely separate one just for the holes. Okay, I know, an equation. But don't let the symbols freak you out. The real power of these new levels is that they let us calculate exactly what's going on inside the chip. For example, if we know the height of the water level for electrons, that's the EFN you see there, we can plug it into this equation and find the precise concentration of electrons at any point in the device, no matter how much is going on. And this right here is the key takeaway. When the device is at rest, those two water levels, those quasi-Fermi levels, are at the exact same height. But as soon as the device turns on, they split apart. And the size of that split, the energy gap between them, tells you exactly how far from balance the system is. A bigger gap means more activity, more current, and more computation. So this theory is all very neat and tidy, but the reality inside a semiconductor is, well, it's messy. Electrons and holes can't just cruise along some perfect, empty highway. In the real world, they're constantly running into obstacles that create basically microscopic traffic jams and impose a hard speed limit. This whole process is called scattering, and you should really think of it like a pinball machine at the atomic scale. The electrons are the pinballs, and they are constantly colliding with vibrating atoms, getting deflected by the very impurity atoms we added on purpose, and even bumping into tiny little flaws in the crystal. Every single collision just knocks them off course and really limits their overall speed. Now, if you push these electrons with a really strong electric field, which is exactly what we do in modern transistors, they accelerate so fast between collisions that they become incredibly energetic. They get so much energy that they're effectively hotter than the silicon lattice around them. And these hot electrons are really fast, but they can also cause problems, like leaking current where you don't want it. And all of this leads to an ultimate speed limit. You can see it right here in the chart. At low electric fields, sure, a bigger push gives you more speed, but look what happens when the field gets really strong. The velocity just levels off. It hits a plateau. At this point, the scattering is so frequent and so intense that the electrons simply cannot go any faster. Their speed has saturated. You can't get any more out of them, no matter how hard you push. All right, so let's put all these pieces together. We have the forced push of drift, we have the natural spread of diffusion, and we know that both of these are limited by scattering and a very real speed limit. It's time to combine all these ideas into one single, unified model that describes the whole thing. And it all comes down to what's called the Drift-Diffusion Model. This is really the workhorse of semiconductor physics. It's the foundational set of equations that engineers use to design and simulate pretty much every modern electronic device, from a simple light bulb to the most powerful processor in your computer. Now, these equations might look a little intimidating, but the story they tell is actually really simple. For both electrons and for holes, the total current, it's just the push from the drift part plus the spread from the diffusion part. That's it. This beautiful, elegant balance is the engine that drives our entire digital world, and it's all captured in just these two lines of math. And you gotta remember, this is not just some abstract theory. This elegant dance between a forced push and a natural spread, all while dealing with real-world speed limits, is happening billions upon billions of times every second inside the processor of the very device you're watching this on right now. Mastering these principles, this push and spread of drift and diffusion, is what allowed us to build the entire modern world. So that leaves us with one final big question. If this is the physics that built our digital age, what new and maybe even stranger physics will we need to master to build whatever comes next?